Lunch? Anybody? Are you awake? Okay. Had coffee? Okay. So, I've seen the word future on quite a few slides these days, and I get the feeling we'll see more of that. Take it away, Peter.
Thank you. So this is kind of unexpected. When I saw the schedule and they had like Jez Humble and Joe Armstrong at the same time as me, I was thinking there'll be 7 people. Like now there are people sitting in the stairs. I didn't expect that. That's good. So I'd like to start out by some sort of understanding of where you guys stand in terms of doing asynchronous stuff. Who's familiar with futures? Listenable futures? A bit fewer. Who use listenable futures every day? Not so many. All right. So this talk is about asynchronous coding in Java in particular, because it's different in different languages. And it's got some sort of microservices twist, because I think it's more important when you're doing microservices than when you're doing monolithic stuff. I guess a lot of people are familiar with Spotify, but I thought I'd share at least some numbers and some things about what we are and what we do. We do streaming music. I think a lot of you may be users. We have about, the public numbers are at least, that we have more than 60 million active users, active in the last 30 days, and more than 1.5 billion playlists, which makes for interesting concurrency problems. We're not going to be talking about that, but updates and stuff like that is fun. And we have more than 30 million songs in our catalog, and we're adding, I think, about 20,000 new every day, every working day. And me, so what I'm doing at Spotify is I'm building infrastructure, and things I've been working with over these 2 years I've been there are things like the service discovery system we use. So when a new service starts running, or a service starts running on some machine, it registers itself with that system, and it's available for clients to call. Some of the routing infrastructure that we have, and also a service development framework, which is sort of like Spotify's version of Drop Wizard, if you know about that. I've been doing microservices stuff for about 6 years. 4 years at a company called Shopzilla, and 2 now at Spotify. Those two are, Spotify's bigger, but they're sort of similar sizes in terms of the deployment infrastructure. So there's a few data centers, a couple of thousand servers, and quite a few small services that are everywhere. And so that you can sort of have some kind of idea of how much you should trust what I'm saying. Like the things I've been doing in terms of asynchronous code are at Shopzilla, the site does about 10 to 40 different asynchronous service calls every time you open a URL on that page. And I was working in the Shopzilla inventory team, which is where you take lots of XML files or tab-separated files, and you put them into a very big database. Get a lot of write, so we were using something called VoltDB for that, and I did some async stuff there as well. And now at Spotify we have something we call view aggregation services, which is sort of similar to the Shopzilla site in some way. Get into that more, and where we're doing also, a few service calls that we need to combine into some result. So what I'm going to talk about is why do you want to write asynchronous code, and why not? And given that you decided that you want to take the plunge and do it, so what are some ways you can do it? Quite a lot of me showing you code in IntelliJ, using 3 different frameworks that you can use for that. Right, why asynchronous? And the only reason I know of anyway is performance. But it's performance in different ways. So when you're doing things synchronously, you limit your throughput to by the work count, and also by the latency of the things that these workers have to do. And also, when you're doing things synchronously, you can be using resources for the wrong things. Like you have a pretty heavyweight thread that's maybe just blocking on some get, an HTTP get or something like that. And you can get congestion, which is another kind of waste you get when you're doing things synchronously. Also, if you're doing things asynchronously, it's easier to get even latency improvements by doing things in parallel, rather than doing one thing first and then waiting for that to do the next. So you're sort of doing less active waiting when you're doing async. I'm going to show you an example. So imagine this is a restaurant, and you have orders coming in. You have a drink station where a waiter puts an order on the drink station, this is some kind of rotating disk, gets processed, and then a drink comes out, and the food station. And then you get it back to the customer. All right? So with 4 waiters, what happens? An order comes in, one waiter picks it up, puts it on the drink station, waits for the result. One more, same thing. So now we have 2 waiters waiting for drinks. And then a little bit later on, you might have a situation like this, where you have all 4 waiters waiting for orders that are in various stages of processing. And of course, the thing that happens is that there's another order. And what do? I mean, either you add latency and don't process that order. You can maybe queue it, and maybe sometimes you need to drop it because the guest leaves or something. Or you hire more waiters, right? Those are your options. So, and it's the same sort of thing with threads and stuff. Like if you let every thread wait until it's completely finished processing one request, and then you need as many threads as you want to have. You know, the number of threads you need is determined by the latency of your processing and the volume of incoming requests. And again, to sort of look at this physical analogy, like if you can't just keep adding waiters. At some point, the floor gets full, and then they get completely ineffective because they just run into each other all the time. And that's context switching, you know, somehow. And if you look at, you know, asynchronous, you can do that in many different ways. But one way of looking at it is like this. So you have one waiter assigned to each station, one that just picks up incoming orders and puts them onto the drink station, one that waits for finished drinks and, you know, moves the order on to the food station, and one that takes ready orders and sends them out into the dining hall. So, and that means that you're not, the number of waiters you need is not proportional in quite the same way, in a way, to the incoming load. Okay, cool. So, and how does this relate to microservices? As I mentioned, I've been working with 2 microservices, so I don't know if that's enough to generalize about what a typical microservices architecture looks like, but this is my experience from 2 places. You basically have clients, and they make calls, and then you have like the backend services, which is, you know, some sort of not very deep graph or whatever, chain or tree of things that call each other. And in my experience, the first layer that the client request hit is a bit special. It's like some kind of aggregation layer where you have much more fan-in and fan-out. I'll show you a couple of examples of from Shopzilla and Spotify how that works. But the thing there is that that's where you do, like in Shopzilla, where you have like 40 requests sometimes that you need to fan out to different services and then combine all the results back again together. And that's something that's particularly hard to do in Java. And that's why I'm doing this talk. And the thing that makes asynchronous interesting in this case is that when you move from a monolithic application, what used to be a method call within the same JVM is now a remote call to some service, which might in turn be calling some other service again. So you add a lot of latency. And when you added latency to that first image where the wait is waiting, then you need more waiters, and then you run into problems with resource utilization and stuff, and throughput. So, Shopzilla. This is me doing a search for digital TV at Shopzilla a couple of weeks ago. And what happens is, so you search, and there's a search engine that finds products that match that search, right? So, and the search engine in its index doesn't have all the information that you see on this page. So that means that once you have the product IDs, you need to take those, you take the result of the search engine, and you send that to some other service that knows about the details of the product. That comes back. Similarly, each product is sold by some merchant, and Shopzilla knows about, you know, merchant ratings and stuff. That's another service. Also, the search engine determines a category that you're in. So in this case, digital TV, that's probably somebody's interested in the televisions category. But there are things that match digital TV in other categories, such as audio and video cables, that sort of thing. This is another service. And again, there is some information which is, you know, attributes of things that are in televisions. So, you know, you can have plasma, LCD TVs. This doesn't apply to socks, but it does apply to TVs, so that's category specific. Also, something that sort of is dependent on the result of your first service invocation. So typically, like in Shopzilla, you have a situation like this, where you first do a search. Depending on the results of that search, you do a lot of subsequent calls to other services and combine the results at the end to the rendering in something that just renders HTML. And at Shopzilla, which is, I forgot to say, it's a price comparison site. It's just like Price Runner, but it doesn't exist in Sweden. So, and something that we found was that latency to start a render is really critical for the amount of money that we made. Because if the site felt snappy, then people would use it more, and it would be a good thing. So the thing that we wanted to avoid was that when we had like a much more complex graph than this, with about 40 invocations perhaps, was that some of these services got in the way of starting to render, starting to send stuff down to the web clients that we're using in this. And therefore, the guys that built this infrastructure, they created a framework for where basically you would get a future to some service result, and you'd put that into a map, and with some sort of well-defined key. And when you got the result out of that map, you'd get the real result. You wouldn't get the future. So it's not quite a map, but it's something like it. It was called a map. And there were some issues with this. One of them was, so if I do a get for this key that I know should be there, and I get a null, why is that? Was it that the service call failed? Or maybe because this is concurrent, like maybe I did it before somebody had time to put the result in, Or maybe the service call actually returned a null. Like, can that happen? We didn't know, and we had bugs. Also, because the get was always blocking, that led to people sometimes blocking the main thread inadvertently. Like you do a get on something, and you don't realize that you're doing this on the main thread, which means you're delaying the start of render, which means we're losing money. And there was a pretty severe lack of visibility because we didn't know what was put into this map. We had there was a bunch of, say, 100 keys that you could use to put stuff in there, but we didn't know for any given page, like what was actually going to end up in the map. Why did I get a null? Maybe because this was distributed all over the code. So I created something that we called page flow, where like the difference was that, because of this visibility issue, I wanted to say, okay, what happens if we create this graph, this call graph, as a data structure? So we actually have, edges and nodes and stuff in there, and the service calls to be made in each node in a map, in a data structure, and then use that. And that turned out to work really well. Like the syntax that I used, or I got help with the syntax especially, was sort of clunky, and it was really tied specifically to the way that we did things at Shopzilla and all that. But it helped clean things up a lot and helped things make things much more understandable. Something that I'm pretty sure was an accident, I don't think I thought of it in advance, was that the concurrency things, they got moved into the framework. All of the concurrency concerns were moved into the framework. So when you wrote something that would be executed in one of the nodes of this graph, you never saw a future, you just saw a result. So your code would only get invoked by the framework when the result was ready. And that turned out to be great because it made it impossible to do this, blocking get that would delay the render and everything. It just made things a lot easier. I mentioned that I worked with the inventory team, and there I created something. We were doing, using something called VoltDB, which is an in-memory clustered database, which has with some limitations, ACID properties and stuff. So it's really nice. You can do really high volume reads and writes. And we were doing about 100,000 writes per second to that database with data sets about 200 million entries. So, it's hard. And we tried to do it synchronously first, but it didn't perform well enough. So we had to go async. And we were doing simple chains like you're seeing on the right there, with basically like some reads and a couple of updates or something. But because we were using futures.transform, don't know if you haven't used listenable futures, you don't know what that is, but you'll see soon. That it's sort of like doing if else and then if else and sort of nesting deeper and deeper. It gets really hard to read and you don't know where you are. So I created a small library for that, for doing these chain demarcations. Simple, just a chain, but it was nice because it was generic. It wasn't tied to any infrastructure or something, and I like that syntax. All right, Spotify. Spotify started out with a very thick client, very intelligent client, doing things like, because latency, when you're playing music, then latency becomes really, really important. You don't want to press the play button and then wait for a second before music starts. Right? It has to happen instantly. Otherwise, it doesn't feel like it's local, and that was one of the key differentiators, I think, of Spotify to other music services when we started. And the way they solved that was by having a really clever client that was doing things like peer-to-peer and had all sorts of logic. Also, initially, Spotify was really only desktop, so you can have heavy clients and you have good networks typically. But that's changed, and now I'm not sure exactly about the numbers, but I think something like 70 or 80% of our users are now on mobile phones, and this, it's a different world. So we started a couple of years ago to move logic from clients into the backend for two reasons. One of them, or for a few reasons. One of them was that we wanted to make it more mobile friendly by having fewer network hops. Like if you're on a desktop with an Ethernet connection, then it's no problem to do lots of small calls and get data. But if you're mobile, then the latency of each of those calls gets really long, and you're using up battery, and it's bad in every way. It's also the case that when you have 60 million users, deploying something to all of them is, it's not easy. But our number of servers is much smaller, so it's easier. Servers is smaller, so it's much easier to deploy to them. So we can make changes more quickly by doing more things server side. So this led to what we call view aggregation services, which do exactly this thing. Like they sort of combine results and package them up into something that corresponds to some sort of UI view in the client, all the data that you need for the view, and some of the formatting as well. And then we saw this thing that when you're doing nested combinations of listenable futures or futures in general, that makes the code really complex, and there's a lot of concurrent or like a lot of stuff in the way of understanding the code. So I created, together with a colleague called Rusbe Delavari, we created something called Trickle, which combines two of the ideas from those Shopzilla frameworks I created. So you're actually creating a graph. Instead of having the graph be defined by your code, it's actually data structure, and it's not tied to any specific infrastructure. It's very generic. So an example of an asynchronous call or a view in the Spotify client, if you type in search, if you type in something in the search box, then you get this drop down, which is the result of a call to the search view service, and it's actually combining the results of about 8 different services. Not in this particular case, but depending on the results, it may call up to 8 services. So here, like the profiles result is from one downstream service, and the rest of the stuff is a combination of 3 services. Right. Why not asynchronous? Because it's hard. I think somebody said fracking hard the other day. And I agree. So, and I'll show you some examples of this as well. It's harder to write, it's harder to read, it's harder to test, and it's much harder to reason about. So Java has some strengths and some weaknesses, and one of the weaknesses is verbose. When you're doing concurrent stuff, the concurrency management overhead can completely obscure your business logic. You don't know what's going on anymore. The fact that the concurrency can be quite invasive. This problem we had repeatedly at Shopzilla, where somebody did a get on the wrong thread, and things didn't blow up so we didn't notice it. They just got slower subtly. There's the problem of fan-in as well. So in Guava, which is a great language, if you have multiple futures, you can combine them into one using all as list, but you lose some type safety, or at least you get some noise. Two of the other frameworks, both Trickle and RxJava, they have something called func 1, 2, 3, 4, 5, and no more. So if you need to combine more than 5 futures, you have to do it twice. In Java 8, there's something called byfunction and byconsumer that allows you to combine 2 futures into one. But in general, it's a little bit messy. And when you're doing things asynchronous, then the testing gets a lot harder. Like you can introduce a lot of flakiness, Exception handling gets harder. I'm not going to talk too much about that, but and you have more possible execution paths because things can happen at the same time. You don't know that your test actually covers, all of the different orders that things can get run in. Graceful degradation is not really a part of this. It's more a part of a microservices thing where, if you're making 8 service calls and one of them fails, you probably not. The thing you want to do is probably not to return a failure to the caller. You want to return the results of the 7 that succeeded and some reasonable default. It's not async really, but it's one of the complexities that you get in this situation. So, code examples. Let's see if this works. I don't know if it does in the presentation view. It doesn't. Can I make this smaller? No. Oh. So apologies for this. Exit full screen. Don't know if it happens if I do this. If it works if I do this. No. So I should have tried this out before. This should go away. All right, I'm just going to do this. Can you guys see this? Yeah? Cool. So this is an example of something that happens, it's not the exact code, but it's the same algorithm from the service discovery system that I'm working with at Spotify. And one thing that happens is that services that are running, they send heartbeats. And this is what we do when we get a heartbeat from some service that's running. We get something called an endpoint, which is basically a combination of host, port, service, and protocol. So we'll say that service search view is running using protocol Hermes on port 5700 and on this host. What we do then is we find out what do we know about this endpoint before. Have we seen this guy before? Whether we've seen it before or not, we now know that this guy is up. So we say, let's store the fact that this guy is up. And that also includes a timestamp. And then, if it turns out that we didn't know that this endpoint was up before, which can be 2 things, like we didn't know about it before, or we knew about it but thought it was down before, then we say that, okay, now that our known state has changed, so we update the timestamp to say that, okay, if somebody's caching this stuff, your cache is now invalid, basically. And then we say, we want to hear from you again in so many milliseconds. It's always 30 seconds, but we made it configurable on the server side, so we don't have to deploy changes to 10,000 servers. So that's what it does. Any questions? No. Let's see what happens if we use listenable futures to make this asynchronous. No, can't see this. Right. Anybody understand it? I think a sane reaction now is something like, what? Or even, what the fuck? This is actually doing the same thing. And if you look carefully, you can sort of see the same stuff here. Like you see the get. You can see that we're putting an entry that's now up. We're doing this if not present, then updating the change, and returning this heartbeat interval millis here at the end somehow. But there's a lot of there's a lot of noise. This is what I mean by concurrency overhead, like getting in the way of the business logic. So let's see, I have some notes here about what to note. So like the way this works, a listenable future is like a regular Java future, but it allows you it calls callbacks when it's done. It doesn't just you can't just do a get and get the result. It actually calls a callback if you want. And that means that the guys at Guava, they built tools that you can transform a future. So that means that as soon as this result is ready, then call this method and return a future that returns a different type. So that's the transform. Using an asynchronous function. And that's what this is about. So the way to chain futures is by using transforms of them. And I say pretend transforms here, because if you're functional, I guess that the transform is like it takes the inputs and returns an output and has no side effects. But these transforms, a lot of the time, you actually want to have side effects. So we have two of them here, like the store.put and the store.update last timestamp. So it's not a transform; it's more like something that happens when this guy's done. Another thing to note is that I've created two variables here that are, or two inputs to functions that are just, that I gave the same name, ignored, just to highlight the fact that these are actually not used. The only reason why we have to send them in, input them into a function is so that we can get that thing to happen after the previous thing. So in this case, for instance, I want the update of the timestamp to happen after the put, just so that I know that it was successful. If it was an exception, that'll just propagate. But I don't actually need the result of the put to know if I should change the timestamp or not. That's only dependent on what the previous result was, like if I knew about this thing before. All right? Let's look at another one. This is the same algorithm in Scala, asynchronous. And there's actually a lot more code here. This is the algorithm. And it's really funny, I think, to look at this, because you see, it looks pretty much, I mean, the syntax is different and all these things. But the structure of the code is exactly like the synchronous Java version. Like, you do a get, you do a put. If it was a change, then register that fact. And finally return the next time this guy is supposed to be back. And that's it. I even have more code here because it's compact. So a lot of the stuff that you get with the raw listenable futures is Java as a language not shining like it can sometimes. So if you look at the synchronous version or a sequential version, this is what that call graph looks like. You have an input, which is an endpoint. You read the current state for that endpoint. You update it to say that, OK, I know it was up now. And then maybe, depending on the previous result here, you might update the timestamp, and then return the interval. But the thing is, what we actually want to do, or if you look at the data dependencies and sort of the causal dependencies of this graph, you have the input is needed both to update and to read the current state, right? We want to do the update after we've read the current state, because otherwise these might race and you might write something before you get a chance to read it. So we might lose track of the fact that that was a change. And the same thing, like here, I only want to do this if I knew that this was OK. And the interval, I don't really need the result of any of these things to return that. It's always constant. So that's what the call graph looks like. You have this sequence of events. Let's look at yet another version of doing this. Rx heartbeats. This is using something called RxJava. Rx is short for reactive extensions. How many are familiar with Rx? Some, not many. It's something that was created by Eric Meyer, who's a pretty well-known researcher. He used to be at Microsoft. I think he may be left. I'm not sure. And there's a link later on in the slides. You can look at it. Look it up. It's pretty interesting. The thing there is that they use something called observable instead of a future, and an observable is like a stream of events of some kind, or a stream of things. And you can use a lot of functional programming-inspired ways of combining these and zipping this and all that. So if you look at the code here, it's much more similar to the synchronous example in the beginning. You do a store.get, and then a put, and then something here, sort of magical. If there was a change, an update, and then return heartbeat intervals in milliseconds. So way less noise than the listenable futures, raw listenable futures version. So much easier to see what's the business logic doing. That's great. Something that's confusing to people, I think, especially people who like me are not functional and more like regular Java programmers, is that the function names or the method names here are functional. So you have flat map, you have zip, you have map. What do they mean? It's obvious if you're used to functional programming. Otherwise, you need to learn it, and you can do that. It's not so bad. Same thing here as with the listenable futures version. You have to ignore some inputs just to get the causality in there, not because you have a data dependency. One thing I think is really interesting is this. So this is methods on observable. Oh, we're S now. We're almost done. No. It begins again. Yeah, now we're done. This is object. It's a big API, and the way they've structured it doesn't really help you to discover it. Like, it's not obvious what you can do at the next step. You can do anything. Like, the world is open. So I think that's like some kind of minus point for discoverability. Okay. Final code example using Trickle, which is a library that I and Roosberg created. So the API method is this one. You get an endpoint, and you say heartbeat graph bind endpoint input to endpoint and run. Okay, weird. And the sort of the meat of the code is in here. Like, it's when you set up the graph. So this is where you define the explicit graph as a data structure, as I mentioned before, rather than having your code be that graph. So you say call the method store.get with the endpoint input, and you get a graph of registry entry. Okay. Call a method that takes an endpoint and does store.put with that endpoint flagged as up. Okay. With the endpoint input after the previous graph. Okay. Call a method that takes a previous entry, a registry entry that's previous entry, and does this conditional check, and potentially updates this one with the result of the previous graph after the up graph. Finally, like, this is the total graph. Call a function with no inputs that returns the heartbeat informulus once the timestamp graph is up. So this is like explicitly creating the graph on the right there, where after is like the dashed line, and the data dependencies are with. Oops, I should do this. So, and what notes did I have here? So it's noisier than Rx a little bit. Not very much, but a bit. It's this graph thing is confusing, I think, to almost everybody that I've shown this to or has tried this. What's a graph? Something to note as well is that you can give a graph a name. Update timestamp, which will help you with debugging. The same thing with the inputs. Like, so that means that if something happens, then you'll in the stack trace, Trickle will tell you the update timestamp method failed, and the inputs were endpoints with this value, and so on. So you get a little bit of troubleshooting assistance. And if we look at, oops, let's see what happens if we try to create this first one. So store get. Oh, I need to provide. I mean, this is a compilation error. Should be. I don't know why syntax highlighting isn't working. Whoa. Okay. Should be. Anyway, what it tells you is that you have to have a parameter of endpoint, and if you just do tab completion, that doesn't work. Oh, there you go. It'll give you that, and then after that, it'll show you like what are the things you can do with the API. You can add like a fallback, which gives you a default value, or you can do it after something, but you cannot add more parameters at this stage, for instance, which is kind of nice. Okay, enough about that. So the IDE will help you a little bit to build your graph. So these are the 3 frameworks I wanted to talk about. And here's a subjective comparison where I tell you what I think about these different frameworks. Listenable futures. A link to some documentation about them, for those of you who are not familiar with them. Things I like about them, they are low level. There's not much magic going on. Mostly familiar concepts, they're sort of easy to learn. I mean, futures are a bit tricky themselves, but once you've got that, then listenable futures is not a long stretch. API is nice and small. There's a lot of useful utilities in the futures class in Guava, for instance, and so on. And futures are common, and they give you like good interoperability. It's usually easy to migrate from something else to using listenable futures. The cons, you've seen the verbosity, and the fact that the concurrency management stuff just sort of hides your business logic or obscures it. Like you don't see it, you just see concurrency stuff. And it's easier to make mistakes as well with that. And then the fanning, that's messy. I didn't show that, but your best option if you want to combine multiple futures is to turn them into a list and then return that. And it's a somewhat a pain in the butt. And if you look at RxJava, here's a link, reactivex.io. Things I like about that, they're very feature-rich. As you saw in the API, like there's a lot of methods, so you can do a lot of things with them. Especially if you have like a stream of data. So if you have something that you make a call and then you get stuff periodically or something like that, then that's really good. They're very good at separating concurrency and business logic, from each other. You don't see the concurrent bits in your business logic. And it's really easy to combine results and do fallbacks. I didn't show you that, but there are methods. So if this observable fails, then return this instead, and so on. Code is clean, I think. Cons, I think primarily the unfamiliar concepts, like you have to understand what observable is, and you have to understand some functional programming. I think there's a fairly high learning threshold. The API, I think it's large and clumsy. And it's all a little bit weird. It's not a big deal. It's like the transforms. Like a transform should be side effect free, but it's not. So not a big deal. And in Rx, then everything is a collection. So even if you're just getting one, you're still getting an observable with one entry in it, and it looks like it could be a collection. Now you don't really know, as far as I know, in the type. The type system won't tell you that there was only one. In fact, there could be. You might think there could be more. And if you look at Trickle, which is open source, I didn't say that, I think. And available on GitHub. The things, I mean, I think like Rx, it separates concurrency from business logic pretty nicely. It's got pretty good error handling and reporting support, so you can, because of the naming thing, it's a bit easier to understand where things went wrong. And it interoperates well with regular futures. Cons, it's not in widespread use, and it's weird to do the wiring in data. While building Trickle, because it's not a good idea to do things just because you think they're a good idea. Like I think we all have tendencies to fall in love with our own inventions, or innovations. So I didn't and still don't trust my own judgment about Trickle. So we did a comparison. We asked some people to do to try building a small asynchronous thing using these 3 frameworks, and asked them to give feedback on what it was like. And these people all knew about listenable futures. They used them all the time. So for them, it was obviously really easy to get going, and they could focus on the core business problem. So get going is how quickly could you get going with this framework? How much did the framework allow you to focus on the core of your business problem, and how much did you have to sort of spend managing the framework, understanding things that you didn't really want to understand? And how clean was the resulting code? And we were quite encouraged to see that Trickle scored quite highly in all of these areas. And I've actually, that async shootout thing is something that I put up on GitHub last week, I think. So if you're interested in trying this out, it's pretty nice. You can go there, and there's like a synchronous example of what the code should be, and there are unit tests for 3 different versions of implementations, and when the unit tests will pass, then you've done it. So you can try it out, and then there's a form you can fill in, and we'll see, the shootout can continue, and we can see what's the best framework for everything. But it's not going to be the best framework for everything. And also, there's a lot more that you can do if you're interested in doing this. There's been a couple of talks here about Akka. which is an actor-based framework. Don't know if people know about Akka? Yes? No? Yes? I think that looks really cool. I think I would take a serious look at that if I would do something greenfield. Now, I mean, at Spotify we have heritage and we have lots of stuff that uses listenable features, so it's not great for us, but I think it's quite cool. In Java 8, there's been some changes. So there's a completion stage and completable future that'll allow you to do some of the things that you do in Rx and Trickle, for instance, in a nicer way than listenable futures. But with this drawback that fanning is a little bit more awkward. I haven't looked into that in detail, but yeah, it's possible. There's also Disruptor, which is something that was built by a company called LMAX for like super low latency trading and really mega high performance. But I think it's not just about that. It also allows you to in a pretty neat way, construct asynchronous call graphs, even if you don't need the performance. I guess the problem with Disruptor is that it's, and I guess with Akka as well, is that there's a lot of learning you need to know, or learning you need to do to be able to use them. Right. So, if you're going to do it, like, how do you pick your framework? Given that there are so many different choices, and I've only scratched the surface, I think, of most of these as well. I think some things to consider are like, what's your migration path? So at Spotify, our migration path to Akka or Rx would be quite long because we have so many libraries that return listenable futures. How do you integrate with third-party tools? What sort of stuff do you get back from them? What's your learning curve, and how often are you going to run into a learning curve? I think it's a really important parameter as well. You know, if Rx, for instance, I think that has a high learning curve. If you're going to be using that every day, that learning curve is not going to be relevant. Like you can get lots of good stuff done because of the cleanness of the code. If it's something you're going to be touching every month, probably not a good choice because you're going to hit that learning curve every month. And also like the expected level of concurrency expertise, like how much you want to force people, I guess, to think about concurrency. If you're okay with that, you know, if you want the performance and you know. You think people are not going to do the gets in the wrong places and, you know, leave dangling futures in places and stuff, then fine, maybe you can just use raw listable futures. Otherwise, you should pick something that's a little bit more high level. But above all, make sure that you need it. Because if you can go synchronous, it's going to be so much easier for you. Async is hard, and it's going to complicate your code unnecessarily. The business logic is probably complicated enough anyway. You don't need the concurrency management stuff in there as well, maybe. If you do, then there are some choices up there. And that's all I had. So we have, I think, plenty of time for questions. Any questions? Yeah? What about the risk of creating a cycle in a graph?
Yeah, when you close the graph.
In Trickle, you mean? Yeah. Yeah, it is a DAG. That's true. So, in fact, the way that we're doing this, you can't, because you need to refer to a previously defined variable. So that means that I can't say refer to timestamp up here because it hasn't been defined yet. So that's the way that we prevented that. There was an earlier version of Trickle that had like a cycle detection built in, but then we managed to sort of tweak the API in such a way that you can't actually create cycles. But that would have been bad. No more questions? So the question is if the services are running in the same VM on different machines. It's all on different machines at Spotify. At Shopzilla, we did virtualization so they could be on the same machine. But at Spotify, we're not doing that yet. So we have, I think, 8,000 servers or something like that. And our average CPU utilization is like 5%. Wow. So, I mean, oh yeah, so the question was, since Scala was by far the nicest version, why don't you just use that across the board? I think that's a very valid choice to make. Scala is. I'm not a Scala expert. I've tried it a little bit. I think it's really complicated. I get some sort of C++ vibes personally from it. And when I was a C++ developer, I shot myself in the foot regularly. And my feet are much healthier now that I'm a Java developer. But I don't know if Scala is. I don't think it's as bad as C++, but you can do really complicated things, and you can make the code really hard to read. At the same time, the code can be much easier to read than Java. So at Spotify, we've made the decision that we're not doing Scala. We're doing Java and Python in our backend services. And the reasons are primarily that we want to limit the number of languages that developers need to understand to move within the ecosystem, and that we need to support in our frameworks and our tools. It's one of the few things that Spotify has actually limited. Otherwise, everybody's allowed to do everything, and it creates chaos. Does that answer your question?